Welcome back, physical science students, to another one of my videos. Today we are going to be focusing on chemical bonds. As you know, we are in the beginning stages of our unit on bonding in general. Last time we talked about balancing chemical equations. Hopefully that went smoothly for you. Again, if you still need help on any of those, do not hesitate to reach out so that we can get those taken care of. Now, one thing I will say, chemical bonding tends to be one of those things that most people struggle with in chemistry. We're going to be talking about two different kinds of bonds, and really, I guess it eventually comes to three different kinds if you take into account some of the things we'll talk about. But either way, let's just get right into it. All right, so we're going to have some new vocabulary coming up. Some things that I want to talk about real quick. Okay, so we've talked about the atom. Okay, so it has a nucleus in the center and it has electrons around the outside. Ions are charged particles, so that means they either lost or gained an electron. And we'll talk about how that results in bonding here in a little bit. Remember that isotopes are atoms of the same element that have different numbers of neutrons. And then, of course, we have electrons, the negatively charged particles in an atom. Neutrons are in the nucleus of an atom, but they are neutrally charged, okay, so they don't have a charge. And then protons are also in the nucleus and they are positively charged. All right, new things. Compounds, okay, that's basically putting two elements together to form something bigger than just the plain element. Okay, chemical formula, we already talked about that in our last video about balancing equations, but chemical formulas are like H2O, meaning water. Okay, chemical bond, that means that two atoms are bonding chemically together, and they're not just being mixed together, they're actually forming some kind of bond. Okay, we're going to get into more about ionic bonds and covalent bonds. Molecules are basically most of they are if the best way to put it is you guys know about the whole like a square is a rectangle, but a rectangle is not a square. So molecule and compound are kind of in that same boat where all compounds are molecules, but not all molecules are compounds. But they are, again, a collection of two or more elements bonded together chemically. Okay, we're going to get into nonpolar bonds and polar bonds, as well as polar molecules and nonpolar molecules with the rest of this video. All right, so let's start with compounds. Some of the matter around you is in the form of uncombined elements such as copper, sulfur, oxygen. Copper, sulfur, and oxygen unite chemically to form a compound. When the conditions are right, the green coating of the Statue of Liberty and some old pennies is a result of this chemical change. The compound formed when elements combine often has properties that aren't anything like those of the original elements. Okay, so basically compounds are just putting together these elements to form something new. And so like that last bullet says, sometimes the result has properties that aren't like any of the individual ones, and so the combination of all of them give us something new. Okay, formulas, like I said, a chemical formula tells what elements a compound contains and the exact number of the atoms of each element in the unit of the compound. So H2O, for example, tells you that there's 2 hydrogen and 1 oxygen in a molecule of water. Hey, just a quick review on ions. An atom that has lost or gained electrons is called an ion. An ion is a charged particle because it is now has either more or fewer electrons than protons. So if it gains an electron, it's going to be negative because it now has more electrons than it has protons. And if it loses an electron, it's now going to be positively charged because it has more protons than electrons. Okay, atoms lose or gain electrons to meet a standard, a stable energy level. Okay, this is all because of those valence electrons that we talked about previously. They want to get down to where they have a stable number Every element out there wants to have a stable number, and that has to do again with the duet and the octet rule, wanting to have 2 in the first level and 8 in every other level to be what we call full. Okay, the positive and negative charges are no longer balanced when atoms gain or lose electrons. When an atom loses electrons, it's positively charged and called a cation. When it gains electrons, it becomes negatively charged and is called an anion. It is the electric forces between oppositely charged particles, such as ions, that hold compounds together. Okay, so if you think back to our charge unit, when we had the attraction between negatives and positives, that is the same forces that keep these bonds together. Okay, so it's still a bond between opposites attracting. Some of the most common compounds are made by the loss and gain of just one single electron. All right, so let's talk about this transfer of electrons. A neutral atom of potassium has 1 electron in its outer shell. That's because it is in the first group. Okay, if you look for potassium, I believe it's number 19. Okay, it's K. This is not a stable outer energy. Okay, what it wants to do is get rid of that 1 and become more like a noble gas who has a full outer shell. Okay, when potassium forms a compound with iodine, potassium loses 1 electron from its 4th level, and the 3rd level becomes a complete outer level. The potassium ion has become, or the potassium atom has now become an ion because it has lost an electron. Okay, so if you think about losing an electron, okay, it is going to become positively charged, called a cation. When a potassium atom loses an electron, the atom becomes positively charged because there's 1 less electron in the atom than there are protons in the nucleus. The 1+ charge is shown as a superscript, that's in the top right corner, written after the element K+, and you can write in the 1 if you really want. Some people don't, some people do. But you'd write K 1+ or 2+ if it was 2. In this case, it's just 1 because we only lost 1 electron. Okay. Furthermore, if I go back up to iodine, iodine is going to accept 1 electron, mostly because it also wants to fill its outer shell. Notice it's on the other side of the periodic table. And what we're going to notice is that there's going to be a lot of bonding between opposite sides of the periodic table, because if you remember our periodic trends, the things on the right want to gain electrons and the things on the left want to give away their electrons. Hey, the iodine atom in this reaction also undergoes a change. An iodine atom has 7 valence electrons. During the reaction, it wants to get to 8. So it's going to take that 1 from potassium and say, thank you very much. We are now stable. Okay? And it is going to become an anion because it's gaining a negative. Okay, so during the reaction with potassium, the iodine atom, I spelled iodine wrong right there. Iodine atom gains an electron, leaving its outer energy level with 8 electrons. This atom is no longer neutral because it gained a negative particle. It now has a 1 negative charge and is called an iodine ion, written as I, and then you can write 1- or just minus in this case. Okay, so how this looks in the Bohr model, okay, this is what I have drawn here is 2 Bohr models. The compound formed between potassium and iodine is called potassium iodide, which is why I kept mistyping it on the previous page. Notice that the resulting compound has a neutral charge overall, but each individual thing is a positive or negative ion because the positive and negative charges of the ions cancel each other out. So what we're saying here is we have potassium. It's got this 1 outer shell ion, if I can find my cursor. Okay. And it wants to give that away so that it can be stable. And so what it does, if you follow that arrow, this iodine has 1, and then it's got 2 right there, so that's 3, and it's got 2 more, so that's 5, and it's got 2 more, so it's 7. Okay, so we're going to add that one to iodine to make it full and to leave potassium full as well. And so you can see over here on the right that they have this positive negative attraction, this bond, okay, because this is going to be a bond because of that charge attraction. Okay, so opposites attract, so a positive is attracted to a negative. And the way that we write that reaction is in your bottom right corner. Let me get a color that I like. Okay, right there. That is how you show the bond between an ionic bond, which we'll get to here in a second. But that is the way with the brackets, with the charges, and then with the full outer shell in the Lewis dot structure for the second atom. Okay, so that was a rundown of the ionic bond. An ionic bond is the force of attraction between the opposite charges of the ions in an ionic compound. Okay, in an ionic bond, a transfer of electrons take place. So literally, one is taking an electron from the other one. Okay, so there isn't any sharing, which we're going to talk about in a little bit. One is literally taking the electron from the other one. If an element loses electrons, one or more elements must gain an equal number of electrons to maintain the neutral charge of the compound. So you can have a situation where one element gives up 2 electrons and you have 2 other elements that each gain 1. That is possible, but the overall charge has to be the same. You can't have something that gives up 2 electrons and then it bonds to something that only accepts 1. Okay, it has to be 2 and 2, 1 and 1, 3 and 3. Has to be the same no matter what. Okay, so the formation of magnesium chloride, for example. So we have magnesium, okay, and 2 chlorides, MgCl2, is another example of ionic bonding. This is what I was talking about with you can give electrons to 2 separate atoms and still be an ionic compound. When magnesium reacts with chlorine, a magnesium atom loses 2 electrons. It is in the second group because it has 2 valence electrons. It's trying to give those 2 away to become stable. At the same time, 2 chlorine atoms want to gain 1 electron each. Okay, so they have 7 valence electrons. They're in the 7th group right next to the noble gases called the halogens. So they want to gain 1 electron each to become stable, okay, to get 8 in their outer shells. And so if I give each of them 1, everybody's going to be satisfied and stable. Okay, they're going to become negatively charged chloride ions because they gained 1 electron. Okay, and so if you look again with my Bohr models down here, I don't know why my cursor disappears, but we've got 1 and 2, and each of them again are going over here, and they're going to fill the outer shells of these chlorine atoms. Okay, and the way that we would write that compound is written right over here. Okay, so brackets with a full chlorine Lewis dot structure. All 8 are shown there. 1, 2 on the top, 2 on the bottom, 2 left, right, with a -1. And then you can have magnesium 2+, and then another chlorine ion on the other side. Okay, so that's how we're going to be writing ionic bonds. Remember again that ionic bonds have to be a transfer of electrons. You have to give them away or receive them to be ionic. Okay, so let's bring back again the idea of 0 net charge. The result of this bond is a neutral compound. The compound as a whole is neutral because the sum of the charges is 0. I've got magnesium that's 2+, magnesium that's 2+, and chlorine that is 1-, but I add another chlorine, which is another 1- to get to 0. I hope that makes sense. So I've got 2+, and and I've got -1, which takes me to 0 net charge, which is what you always have to have in an ionic compound. Okay, all the charges have to cancel out. When atoms form an ionic compound, their electrons are shifted to the other atoms, but the overall number of protons and electrons of the combined atom remains equal and unchanged. Therefore, the compound is neutral. Ionic bonds usually are formed by bonding between metals and nonmetals. Okay, so just like I said, you bond mostly with the things on the left to the things on the right of the periodic table. Okay, things that are in like the first group or second group bond with the things that are in the 6th and the 7th group. The halogens like to bond with the alkali metals because each of them has 1 to give or 1 to gain, and that keeps us here at 0 net charge. All right, so let's talk about molecules real quick. Some atoms of nonmetals are unlikely to lose or gain electrons. For example, the elements in group 14 of the periodic table have 4 electrons in their outer levels. They would have to either gain or lose 4 electrons in order to have a stable outer level. The loss of this many electrons takes a great deal of energy. Therefore, these atoms become more chemically stable by sharing electrons rather than losing or gaining. So what they're saying there is there's a point in the periodic table. Okay, so we have, for example, the alkali metals that have 1 valence electron. We have the alkaline earth metals that have 2. We have the halogens have 7, and so on. There's a group in there that has 4. So it's kind of right in the middle. It wants to have 8 or go back down to 0, so the next level down has 8. And so it takes a lot of energy to either gain 4 electrons or lose 4 electrons. So instead of losing or gaining, they do something different where they share it with other ones, and it forms outer shells that are all full. And when they do that, that is called a covalent bond. Notice the words in here. Co, okay, co like cooperating, okay, so with other things, okay, basically being a team, and valent, okay, valence electrons. They will be sharing valence electrons. Okay, that's literally what the word covalent means. Okay, they're taking valence electrons and they're cooperating with them. The attraction that forms between 2 atoms when they share electrons. Notice the difference. Okay, ionic bonds formed by giving electrons from one to the other where they become charged. Covalent, they will be sharing electrons. Make sure you write that down. That will be on the test. A neutral particle that forms a excuse me, a neutral particle that forms as a result of electron sharing is called a molecule. All right, a single covalent bond is made up of 2 shared electrons. A water molecule contains 2 single bonds. In each bond, a hydrogen atom contributes 1 electron to the bond of the oxygen atom contributes the other. The result of the type of bonding is a stable outer energy level for each atom. Okay, so you'll notice here, okay, that oxygen has 6. Let me see if I can find a pen that I can actually use. Okay, so we have right there, I'm just going to circle them. Oxygen has 1, 2, 3, 4, 5, 6. Okay, 6 valence electrons. So it wants to get to 8. Okay, hydrogen, I'm going to star these ones, has 1. Okay, so technically it wants to get to 2. That's the duet rule. Okay, so the first outer shell that it needs to fill, it has to have 2 before it can move on to 8. So it wants 2. So what they do is they go in here and they share electrons. So they form this bond where they're sharing these electrons so that both atoms are happy and stable. So now if you count them, oxygen has 2, 4, 6, and 8. Okay, and hydrogen here has 2, and this hydrogen here has 2. Okay, so that's the whole idea with covalent bonds, is the sharing of electrons to fill outer shells, not the giving. Okay, oxygen is not giving anything away to hydrogen. Instead, it's pulling these hydrogens in to share their electrons to fill outer shells. Okay, and you can also have multiple, so you can definitely bond to something and share more than one electron. So a covalent bond also can contain more than one pair of electrons. An example of this bond is in the bond of O2. Okay, so regular oxygen. Okay, remember that oxygen has 6 and 6. So what it does is it shares 2 electrons to both parties. And so what ends up happening is, for example, this oxygen has 2, 4, 6, and this 8 that the other 2 is supplying. And then the other oxygen has 2, 4, 6, and 8 that it's sharing. Okay, nitrogen has to do even more work because it only has 5. So then it shares its 3. Okay, it has 3 valence electrons there, 3 valence electrons there. So now nitrogen here has 2, 4, 6, 8. And then this one has 2, 4, 6, and 8. And so everybody ends up stable and happy because on their own, they are still wanting to gain electrons in order to fill those outer rings. Okay, a nitrogen atom has 5 electrons in its outer energy level and needs to gain 3 electrons to become stable. It does this by sharing its 3 electrons with another nitrogen atom that also has 5 in its outer energy level. When each atom contributes 3 electrons to the bond contains 6 electrons, or 3 pairs of electrons. You can see that in this image in the bottom right, where you have 3 pairs, 2, 4, 6. Each pair of electrons represents the bond. Therefore, 3 pairs of electrons represent 3 bonds, or what we call a triple bond. Okay, so if you look back at O2, it had a double bond. If you look back to H2O, it had 2 single bonds. Okay, so when you only share 1 electron, it's a single bond. If you're sharing 2 pairs of electrons, it's a double bond. And if you're sharing 3 pairs of electrons, it's called a triple bond. All right, so equal sharing versus non-equal sharing. A non-polar bond is a covalent bond in which electrons are shared completely equally. So what we mean by this is we're going to have certain bonds and certain compounds and molecules where one of the atoms dominates the other and it ends up pulling electrons closer to it, causing one side to be slightly positive and one side to be slightly negative. That's going to be in polar. Okay, so I'm going to have some kind of pole action. In nonpolar, there is a perfectly equal amount of sharing. For example, in that O2, in that N2, those compounds, those two are nonpolar, okay, because there isn't going to be a one atom that dominates because it's so much bigger than the other atoms. In H2O, like water, the oxygen is much bigger and has much stronger pull than the hydrogen, which causes it to be polar. The oxygen is going to be slightly more negative because the electrons are going to be pulled in closer to it, and the hydrogens are going to represent the more positive side because the electrons are leaving it slightly. Okay, and so unequal sharing, like I said, electrons are not always shared equally between atoms in a covalent bond. The strength of the attraction of each of these atoms is related to the size of the atom, the charge of the nucleus, and the total number of electrons the atom contains. Okay, so all three of those can kind of affect this sharing and unequal sharing. So what this results in is positive or partially charged molecules. One example of this unequal sharing is found in the molecule of hydrogen chloride, HCl. So when hydrogen bonds to chlorine. Chlorine atoms have a stronger attraction for the electrons. Okay, they are bigger, they have higher electronegativity, they're going to pull things into it more. And so what ends up happening, even though these two are being shared, so that hydrogen has a full outer shell and chlorine has a full outer shell, chlorine is slightly negative, or that end is slightly negative, and then the hydrogen is slightly positive. And so this is what we're eventually going to call a polar bond or a polar molecule. Whenever we have this result of unequal sharing, it's what we call polar. Okay, polar. And you can think of that also kind of like when we talked about magnetism, when you have a north and south pole. Whenever you create some kind of charge on one side and charge on the other side, we call that polar when we are talking about atoms. Okay, as a result, the electrons shared in hydrogen chloride will spend more time near the chlorine atom than near the hydrogen atom, which again is why that's going to be negative and the hydrogen is going to be more positive. Okay, and so finally we get to our last slide and our last definitions. The charge is balanced but not equally distributed. This type of molecule is called a polar bond. A polar molecule is one that has a slightly positive end and slightly negative end. Although the overall molecule is neutral, water is an example of a polar molecule. Non-polar molecule is one in which electrons are shared equally in bonds. Such a molecule does not have oppositely charged ends. So we have talked about 3 bonds. Okay, 1, ionic. Okay, 2, nonpolar, covalent, and 3, polar covalent. Okay, so really, we've talked about 2 types of bonds, ionic and covalent, but then covalent kind of gets split into 2 subcategories where we have equal sharing and unequal sharing. Either way, they're sharing electrons, and that's all you really need to know for covalent bonding. We're going to be doing more of this, not only in the next assignment I'm giving you, but also in following assignments when we're going to have to be drawing Lewis dot structures for these covalent bonds where they're sharing electrons and stuff. So be prepared to continue talking about bonding, because after all, this is the bonding unit. And thanks for watching.